All right, we're live. Welcome to the .NET Community Stand-Up. So I'm joined today across the world by James Newton King. So welcome back, James.
Thank you. And today I'm going to be talking about gRPC and performance.
That sounds quite exciting. Those who have been around for a bit will know that we start always with the community links, so I'll jump right into those. My name's Sean Galloway. I'm a PM on the .NET community team. So let's jump right in here. I will do the screen sharing and I will share the right screen because I like to do that. And it is this one. And I will. Okay, wonderful. Cool. So I just shared them over in the links or in the chat. I'll share again at the end. And so here we go. First one up. This is the ASP.NET Core improvements, .NET 6 Preview 2. Some really cool stuff in here, including, of course, lots of like Razer and Blazor stuff lately. So we've got Razer compiler updated to use source generators. This is kind of mind-blowing to me. So this is just really cool. It's using source generators and compiling ahead of time, like during the compilation step, and you know, big performance improvements already. So some other cool stuff in here, including CSS isolation. So we saw CSS isolation before in Razer, and it's good to see this also in MVC and Razer pages as well. So allowing to componentize your CSS. So that is good. And there was one other thing in here, I forget. Preserving pre-rendered state in Blazor is cool. And nullable annotations in SignalR. Nice to see nullable just kind of bubbling throughout things. So,
yeah, we've got quite a long process going on, adding annotations to everything in ASP.NET Core. There's a lot of code, and we're getting there. So the aim is to do everything in .NET 6.
Oh, okay, cool. Yeah, it's a ton of I've seen like pull requests come in and stuff, and there's these pull requests with thousands of lines of code changed and all the things you have to check and stuff. So cool. This is just, I've been reading this book lately from Jürgen. We featured several of his blog posts along the way. as he was writing the book. It's newly updated to ASP.NET Core 5. So, and just all kinds of, what I like about this is it just goes into all the different ways that you can customize ASP.NET Core. So all the way throughout the stack, different middleware and hosting and action filters and just all the stuff. So really cool level of depth. It's been neat seeing, over the years, the community has been writing some really great posts, but it's great to have in one book that I can pick up, and it's all cross-referenced and indexed and stuff. So this is just a great resource. So this is cool from Rahul. Actually, let me switch over and I will show this so people can get the links if they didn't get them earlier. So Rahul's got a series, and this one he's going through JOT authentication and ASP.NET Core with Azure AD. There's a lot of things to set up. He shows going through and writing up the application. He shows the configuration options in Azure AD, and walks through the steps of actually getting it all set up. And then he actually goes in and shows, like with Fiddler, like going in and inspecting. So seeing the flow as you go all the way through. So this is part of a series that Rahul's been doing, and just really good quality screencasts on this. This is a nice one to see. So, Yutang just posted about this, and this is about app service Apex domain support. So these are managed certificates and support for all the stuff, including like auto renewals and everything. And so it's just something you can click through and do directly in the portal as you're setting it up. It's also something that you can automate with ARM templates. So this is really cool. There have been different ways to kind of hack this together in the past. It's really great to just see first-class support. I have seen some people on the Twitter conversation, somebody said it's not working. And, in some cases, it does take a little time to provision. And some of that stuff is covered in this FAQ, but yeah, overall, just really cool. So.
Is this like a alternative to using Let's Encrypt?
Exactly. Yep. So Let's Encrypt is fine, but you do have to do some work to set it up. I've seen, like there's extensions and things to do the auto renewal stuff. And this is just something that's just kind of built in. So
nice.
Yeah. This is just a tweet that I saw go by. So Ralph is saying that there's a survey. I've been posting a ton of surveys in our community links lately. This one is interesting. This is about just an upcoming experience for a cloud-hosted or cloud-native applications. One thing that jumped out at me with this too is that they're actually offering to compensate. So you can go through and depending on your level of involvement, they'll actually compensate you for your time in looking at this. So seems neat. Niels, I saw Niels on the chat earlier. So he's been doing this series, and it's just really cool. This walkthrough of all the different ways that you can host Blazor WebAssembly, static applications. And so, they're static, but then there's other things you need to do as far as like front-end routing and all that kind of stuff. And so he walks through and shows this on Cloudflare pages. Cloudflare is pretty neat because you have that kind of local CDN distribution. Everything's, like optimized and what edge distributed. So pretty cool there. So he walks through showing how to set that up, how to deploy it using GitHub, which I actually wasn't aware that they have that level of integration for Cloudflare pages. So that's neat. And then also he's got a little bonus at the end showing something pull request previews as well. So you can go through and every pull request you can get a preview URL. So anyhow, neat stuff. This is just kind of cool. This is from the .NETos. They've been doing these conferences. It's a very low level conference where they're talking like, very like under the hood stuff and, optimizing GC and async and all kinds of stuff. So this is neat. They've got these infographics that you can print out, which is some pretty in-depth stuff. You can put these up on your wall and people will know how smart you are. So that's very important.
I used to have the ASP.NET Web Forms lifecycle poster
Yeah, good times.
near my desk in my office, and that wasn't to show how smart I was. That was just so I could make sense of it. It was very big.
On pre-render view state and all that stuff.
on init, apply,
Nice.
post back, phase 1.
Oh man, nightmares. So Khalid posted here on hosting 2 ASP.NET Core apps in one host. And so the idea is like if you've got, say, a front end site and then a dashboard. So you can actually, using the console host, he shows how, you can configure multiple hosts using the create host builder. And so the standard uses a synchronous, and it'll just die when it'll run the first and wait. So he uses a task.whenAny and runs them both. This is one of those things where I always read the doc several times to make sure I'm doing it right, because I'm always worried I'm doing something wrong. But my best memory is that whenAny is the right way to do this sort of thing. So cool. And then once he spins that up and runs it, then he's got the app listening on 2 different on the different ports and stuff. So pretty neat. This is kind of building on. So Steve is going a little deeper with the stuff that Brady and I covered a few weeks ago on generating clients for using an open API spec. So he digs, really deep into it. So thanks for the link over to the show that we did. And then he talks, like in depth, goes into the docs. He explains some gotchas that you can run into, depending how you have your directory props set up. And then looking in depth at the ways you can customize it, including stuff like the NSWAG documentation, all the different kind of options and customization opportunities there. So I really like that. The generation is built on top of these tools. So it's surfaced inside of Visual Studio and Visual Studio for Mac, but it runs on top of the .NET Open API command, which runs on top of the nswag command. So you can really get down there and customize it as much as you want to. So good stuff. All right. So this is a cool one from Thomas. Just a quick pointer to a NuGet package you can pull in. Called Pwn Passwords, and this integrates with the Have I Been Pwned website, and it will check as somebody is logging in, is creating an account, and it'll say whether or not that password has been compromised. There's some neat infrastructure too behind the scenes with this. I forget the exact spec, but there's a way that it sends a hash of the password. So it's not transmitting your password up. It's just saying, here's a hash of the password. There's like some sort of agreement that these different, security people have for a way of like transmitting password hashes. So that's pretty cool. And finally, just including this link. So this is a thing that you wrote up, gRPC performance improvements in .NET 5. And so this is what we're going to be talking about today.
Yep.
So
that's right.
That's it for me. Awesome. So this, you wrote that post up for .NET 5, and then of course, things always keep marching forward. Or is there work kind of continuing going on in that?
Yeah. So the big push for performance with gRPC was in .NET 5. There hasn't been much work done directly for gRPC and ASP.NET Core since then, but there have been improvements in Protobuf serialization since then. And one of the demos I'll walk through today will show some improvements we've made since .NET 5. But Protobuf, it's a third-party library. It's available now, so it's not strictly part of .NET.
Cool. All right, let's bring you in there.
Cool. So first, I'll just start off by talking about what is gRPC for anyone who isn't familiar with it. If you've already seen this before, just bear with me for a couple of minutes. So it's a popular open source remote procedure call framework. RPC frameworks make it easy for apps to talk to each other. You can think of WCF as another RPC framework. REST, you can kind of use like RPC, but like it's got state and representing entities instead of method calls. gRPC, it's run by the Cloud Native Computing Foundation. It's the CNCF. And what Microsoft has done is we've written a new implementation of gRPC for .NET using all the latest and greatest tools hosted on Kestrel. And we've contributed it to the CNCF. So we're working together with them to make gRPC good in .NET.
Quick question as you're talking about that, sorry to jump in already, but how much overhead is there? How easy is that kind of interaction in working with CNCF and gRPC?
It's been really good. I think we reuse a lot of the tools that they make. So for example, we use their code generation tools. We build upon their base API. So the APIs between the original .NET implementation and the new one that we've written, they're very, very similar. And we work quite closely with them. So every week we have a meeting with them and we discuss what we're working on, what they're working on, things we should work on together. And we just keep in touch on a weekly basis.
Cool. Okay.
So gRPC is supported by every major programming language. So C++, Java, Go, Node, Ruby, Python, C#, you name it, there is a gRPC implementation for it. And the gRPC team maintains most of those, and we maintain our new .NET implementation. gRPC, it's contract first. So messages and methods are defined in a contract, and then that contract is used to drive code generation. gRPC, it's not new. It was originally open sourced in 2015, but it's the union of two modern technologies. So it uses HTTP2 as its protocol layer, and it uses Protobuf to serialize messages and also as the contract language. So fundamentally, gRPC is another way for apps to talk to each other. A client app calls the server and it gets a response. So the first difference between gRPC and RESTful APIs is HTTP2 is required, and rather than sending text-based JSON as the message, it sends a binary protobuf message. So the bigger difference is how gRPC apps are written. So gRPC is contract first. So the first thing you'll write in Visual Studio will probably be your proto file. And this is where you define the services and also your messages. You can think of writing a proto file like writing an interface, and then your server will implement that interface and your client will call that interface. So from that proto file, we get some code generation happening both for our server app and our client app. And this makes gRPC really productive to use because you don't need to write the client and all the messages. That's all done for you. So you don't have to. And because the proto file is language neutral, you can give it to someone who is writing a gRPC client in a completely different language, say, for example, C++. They can use the gRPC tooling, generate a C++ client, and call your .NET gRPC server. And I've got some more detail here, like breaking down the differences, but I'd really summarize it as gRPC is focused on performance. Protobuf and HTTP2 are binary protocols. They're designed for computers to read and write really fast compared to text APIs, which are more human-focused. And also, gRPC has great developer productivity because of that proto file and the code generation. Meanwhile, HTTP APIs, they're very easy to get started, and they bring across the widest possible audience because every computer, every device is able to talk HTTP 1.1 and JSON because they're just text-based formats.
Mm-hmm.
So let's talk about what work has gone into gRPC for performance in .NET 5. So the biggest improvements have come from optimizing HTTP2 and HTTP client and Kestrel. So we've worked to reduce latency, improve concurrency, remove allocations. And all of these improvements are great because every app that is using HTTP2, regardless of whether it's gRPC or not, benefits. So you could be doing RESTful JSON APIs and you're using HTTP2, you're still going to get these same benefits. So something to call out in particular is we reduced server allocations by 92% when using HTTP2, which is quite amazing. And I'll talk a bit later about how we did that.
Yeah.
Also in Kestrel, we now support Hpac dynamic compression of response headers. So Hpac is a standard that's built into HTTP2, and it's how you can reduce large HTTP headers that are sent with every request and response. Instead of sending the entire thing every time, the entire header is sent once, and then after that, just a very small identifier is sent for HTTP headers. So there are bandwidth savings there and also some CPU savings. We found that it was actually faster to just calculate and maintain a dynamic cache and then write an ID to a response than it was to write the entire header every time and have to worry about encoding and data transfer and stuff like that.
Continually transferring back and forth between strings and
and also just if you think about an ID, like it just might be a bit in size, writing that to the response is going to be much faster than having to take potentially a kilobyte long HTTP header and having to check every single character and encoding every single character. So there's bandwidth savings there, and also CPU savings, both on the client and on the server.
Wow.
And finally, we've worked with the Protobuf project. They write the serializer that we use to serialize and deserialize Protobuf messages for their serializer to support span of T. So rather than having to allocate a byte array every time we want to serialize or deserialize a message, and that byte array will contain all the data that we're working with, we're able to read data directly into Kestrel request buffer, serialize directly from that, and then do the inverse when we're writing the response. We're able to serialize directly to Kestrel's response buffer and then flush it directly to the client.
Wow.
Yeah, and that's especially important if when you realize that previously we were having to allocate a buffer which would contain the entire message that you were sending. So if you were potentially sending a 4 megabyte message, which is very big, we would have to temporarily allocate a 4 megabyte byte array, serialize to it, write it to the response, and then just immediately throw it away, which would cause havoc if you're having to worry about the large object heap and garbage collection and stuff like that. So it's a big improvement.
Wow.
So actually breaking down, comparing .NET Core 3.1 to .NET 5, we increased server requests per second by 65%, and client requests per second increased by over 200%. So significant increase. So that comes from the range of improvements, reducing latency, improving concurrency, which can be a big deal with HTTP2. I'll talk about that in a second, and the allocations that I mentioned.
So in order to, like, if I had a previous service written in 3.1 and I moved to 5, like how big of do I have to do a lot to take advantage of those changes, or is it kind of just automatic?
It's just automatic. It's just like all you'll need to do is update to .NET 5 and just update your NuGet packages to the latest version, and it would just work. Like these are just fundamental low-level improvements we've made.
Nice.
So this graph here is from a community-run benchmark comparing gRPC implementations against each other, and you can see gRPC on .NET highlighted in light blue, and we sit at the top with other fast implementations like C++, Go, and Rust, and Rust is the only one which we are second to.
So this is actually faster than C++. I mean,
yes.
It's close, but wow, that's amazing.
Yeah, well, it's like people think C++ has to be fast, like
yeah.
But really, when you're thinking about gRPC and HTTP2, it's really about the quality and like the algorithms that are inside your HTTP server. Like if you're coding in C++, you can still do really dumb things. Not saying that they've done dumb things or not, but it's about just identifying those bottlenecks and working to improve them.
It's funny you mentioned this because there's a recent thread that I saw on Hacker News, and it was about Grand Theft Auto, and it was a long startup time. I don't know if you saw that, but it was and they dug into it, and they're like, why is it taking so long to start the application up? And it came down to something near and dear to your heart, parsing JSON. And it was parsing a 10 megabyte JSON file, and it was doing it by counting one character at a time. And so this guy just hacking around was able to, without the source code, he'd like decompiled stuff, and he got it like 70% faster. And they've actually paid him out of their bug bounty program. They paid him $10,000, and they're going to be shipping that fix. So, so it is true. C++ is like not a magic bullet, and it's not necessarily faster, and you can shoot yourself in the foot there. But
and I have no doubt that that team who was working on GTA probably tested the JSON parser when it got released, and that 10 megabyte file was probably a few kilobytes, and it was really fast. Like just as the data grew, like there was just that one weak point which caused performance to go out of control. And that can happen whatever language you're using and whatever implementation you're using. Like it'd be very possible to change what particular parameters are being tested in this gRPC benchmark and create a completely opposite result where C++ and Java absolutely smoke .NET. It's just like where your strengths are, and like once you identify you're slow in some point, you just focus on making it faster.
Cool. I had a few questions pop in. You mentioned HTTP2 earlier, and is there what's the kind of status on support of Azure App Service and gRPC and HTTP2?
Yeah, it's a tricky thing to support. HTTP2, you need it to be supported from end to end. So if you have a client might support HTTP2, a server app might support HTTP2, but like if there are proxies sitting in the middle, they can cause issues because they're like intercepting HTTP requests and rewriting them and like sending them out between doing load balancing and stuff like that. Last I heard, they're working on it, but I still don't have a good answer that I can speak to on that at the moment. So what we have done is our gRPC implementation in .NET has really good support for gRPC Web, which allows most of gRPC, most of the gRPC functionality, but allows it to work with HTTP 1.1. So that's an alternative you can use today. Another alternative is you can use AKS, and when you do that, your data and your requests aren't going via built-in Azure load balancers. You sort of manage that yourself. So that's another option. Okay.
You mentioned gRPC Web, and of course, the obvious thing is like access from browser client. Is it possible to use gRPC Web from a non-browser?
Yeah, definitely. Okay. I think the .NET client is probably the only client that supports gRPC Web apart from the JavaScript client. So basically what that means is you can take the .NET gRPC client, you can run it inside a Xamarin app, and you can make gRPC web calls from your Xamarin app to your server and get a response successfully. And that allows you to use pretty much all of the functionality of gRPC, and a lot of the performance benefits like Protobuf, like your messages will still be using Protobuf on devices that don't support HTTP2. So another example of that is Blazor WebAssembly. Blazor WebAssembly, it's .NET, but it's sitting inside the browser, so you only have HTTP 1.1 support, but you're still able to use gRPC Web from that environment.
Okay. Cool. All right, I'll let you get back to it.
Cool. So let's go into a bit of detail about what we did in .NET 5. So the first thing to think about is what actually impacts HTTP2 and Protobuf. Like what are the constraints? Because if we're making performance improvements, we don't just want to just start making changes about what we think will make it faster. We want to first measure and then change.
Mm-hmm.
So gRPC itself, it's a very lightweight framework. Pretty much all the real work happens at the HTTP2 layer and Protobuf. So it's the efficiency of our HTTP2 and Protobuf that determines how quickly we can send and receive gRPC. So what we care about are allocations. How many objects are we allocating? How much data are we allocating? And how much time is spent doing garbage collection? Because time spent doing garbage collection and CPU time spent doing that isn't CPU time that is spent doing HTTP2, Protobuf, and serving gRPC requests. We also want to think about CPU usage. How efficiently are we processing HTTP2 frames and Protobuf messages? We need to think about thread contention. So HTTP2 is multiplexed. That means you can have multiple requests happening simultaneously over a single connection, which is great because you save the number of connections you use. But it means you also need to think about connection bottlenecks. There are places with multiplexing where you can only do one thing at a time with one request at a time. So you need to focus on making those bottlenecks as fast as possible. And then there's also network usage, minimizing the amount and size of HTTP2 frames that are being sent over the network. So an example of that might be reducing header frame size by supporting Hpac compression and dynamic compression. And to do that measuring, there are a lot of choices when it comes to .NET profilers. The ones built into Visual Studio are very easy to use, and I'll briefly demo using the results from a profile result later. There's also the .trace and .memory profilers. They're also very good. They don't come with Visual Studio. You need to pay some extra money to use them. But overall, I think the UI in them is really great and easy to use. And the final one I'll call out is PerfView. PerfView is very advanced, but it's also very tough to master. The UI was definitely designed by a programmer for programmers. And if you're not familiar with performance profiling, it's very difficult to use. People who are good at PerfView are always in hot demand across Microsoft internal teams to help us debug and improve performance in our apps and also frameworks. And I think I'll just call out before I jump into a demo that there's a lot of different approaches to doing performance profiling. Some people have knowledge with using .NET profilers, others use dump files, other people will be good at improving performance at an IL level. So when it comes to performance, the more eyes you get on a problem, the more perspectives you'll get and the more people who are able to improve performance. Quite often I'll look at something and I'll say, this is as fast as I know how to make it. Do you want to take a look and see if you can add your knowledge to doing performance improvements? So what I cover today is some approaches I generally use, but they're certainly not the be-all and end-all of doing performance improvements in .NET.
Whenever I see profilers, I always think of analyzers too. Are there analyzers that will help me see if I'm writing can I mess things up or write inefficient code in my gRPC service or client that would be caught by an analyzer? Or
we don't ship any analyzers for gRPC with the gRPC project or with ASP.NET Core. There are general analyzers built into Visual Studio itself that the runtime team makes that will do analysis of your code and let you know if you're doing something wrong. So for example, a good example is if you call a asynchronous method and you don't await it, an analyzer will probably pop up and tell you, hey, are you sure you meant to do this? And as we get further and further into polishing .NET Core, .NET 5, we're writing more and more analyzers that will check what you're doing and see whether there's a better way of doing it. Like perhaps you might do a substring, and an analyzer might come along and say, hey, what you're doing here, you could probably just do using spans and slices and avoid the allocation from a string.
Okay. One other question is nullability. We talked about nullability earlier with SignalR. Is there any like nullability impact or support in gRPC?
Yes. So the gRPC library is annotated with nullability attributes and has been since the first release. I think there are plans to add nullable attributes to the generated code, but we haven't done that yet. So that would be the place still to do. But for the actual gRPC libraries and NuGet packages, those have nullable attributes.
All right. Okay, well, I'll let you get to your demo. Just
Cool. So the first thing I'm going to talk about is analyzing Kestrel server allocations, particularly around HB2, and how we introduce the pooling of HB2 streams to dramatically reduce allocations. So here in Visual Studio, I have open the Kestrel solution. So Kestrel is our HTTP web server for ASP.NET Core. It's written in .NET and C#, and we're just going to take a look in some of the internals and see what we can do to improve its performance. So if you're ever interested in doing some performance analysis in Visual Studio, what you can do is you can come up to the debug option up here, and there is a performance profile option. So I think most people are familiar with starting an app with debugging and hitting breakpoints. So performance profiling is similar, except instead of starting it with debugging, we're starting it with Visual Studio gathering statistics. So here you would just select your startup project, and then you would choose what exactly you want to measure. So .NET object allocations is one I commonly use. Another one is CPU usage. In this case today, we're going to look at allocations. So I would check this. I would click Start. gRPC app would start up, and then I would get a client to make some requests to the server that would gather some statistics. Then I'll click Stop, and then I would analyze them. I'm not going to do that today just because I don't want to put a whole bunch of load on my computer while presenting. Yeah. So I've got some results here all ready to go.
So those results you have there, are those easy to like share with team members or that kind of thing?
Yeah. So I made this measurement actually like I think 4 months ago when I originally wrote that blog post. I just saved it as this file, I'm guessing diagnostic session suffix, and just to demo to you today, I just opened it back up again, and I've got all the data ready to go. So nice. It's just a matter of sharing these files.
Cool.
So the results here, there's a couple of different panes. The one we'll focus on first is live objects. So live objects is how many objects are currently live and allocated in your app. So here we can see our app when it first started. This is a gRPC server app. So when startup happened, we got a bunch of allocations, and then we didn't have any load. And then at this point, I started sending gRPC requests to the server. So this is demoing 50,000 gRPC requests and what happens to memory usage. And here we can see our allocations slowly build up. So you can see that in this sort of delta down here. Our allocations are built up until we get to this point where they suddenly drop off. So this is where garbage collection happened. This is where .NET decided it needs to free up some memory. So it spends some time analyzing what objects are no longer used, and then it throws those all away.
And then this is that classic sawtooth that you see. Like we've had other people on recently show us this exact same graph. It's that sawtooth where you build up allocations and then you garbage collect and you do it all over again. So yeah, and then the goal is to allocate less so that you don't have to garbage collect, right?
Exactly. So the goal isn't to completely remove garbage collection. It's just to reduce how often it happens. just the time spent doing garbage collection, it just takes CPU cycles, and it's better to spend that time serving gRPC requests than doing something we don't need to do. So if we reduce the amount of garbage we create, we reduce how many collections we have to make, and the amount of time spent doing GC.
And
so
does your gRPC service like essentially stop during GC or just slow way down due to CPU usage?
So these particular garbage collections, they'll be Gen 0. So that means like there are generations of object lifetime. I can't get into it all right now, but these ones won't stop anything. Your app will keep running. I'm not even sure whether your app will pause during a Gen 2 GC, which is like the worst one, which takes the most CPU. Like we might not even need to pause with that, but I'm not a GC expert, so don't quote me on that. But like GC, I wouldn't be afraid of it happening. You just want to minimize it where possible. So yeah, this is this sawtooth graph. This indicates we're doing a lot of allocations, and fairly regularly we're needing to do garbage collection. So down here in this allocations pane, we get a breakdown of what exact types are being allocated and where all the memory is going. So this is descending by bytes. So pipe is our biggest culprit. Then we've got HB2 stream, and then we've got a whole bunch of strings, which are really popular but don't take as much space. So they're a bit lower compared to pipes, and so on. So something which jumps out to me immediately when I look at this list is there's very little here that has actually got anything to do with gRPC or what our app is doing. In fact, the only one is this server call context. So this server call context is allocated once for each gRPC call, which makes sense because we've got 50,000 of them and we made 50,000 requests. But this is the only actual gRPC or app-related allocation. All the rest of these are coming from Kestrel and how Kestrel is managing its HTTP2 requests. And the biggest one, the one which immediately jumps out, is this HTTP2 stream. So you can think of stream as like the HTTP2 representation of a request. When you are a client and you connect to when you make a request to an HTTP2 server, you'll get a connection created. And then on that connection, for each request you make, a stream will get created on the server. And that stream will be bidirectional. So it will process your incoming HTTP2 frames and outgoing HTTP2 frames. But it's sort of like the heart of an HTTP request. And then what we were doing in .NET Core 3.1 is once we had finished with an HTTP2 stream, we would just throw it away, and when the next request came in, we would create a new one. And then eventually those streams we threw away would get garbage collected. And from this stream, a whole bunch of other types hang off it. So there'll be request and response pipes. Strings will be allocated as headers. We've got a request, HTTP request headers collection, response headers collection. This dictionary is probably also related to headers. This is related to buffers and pipes. This looks like an async state machine. More header stuff in the frame writer, more pipe stuff. So there's a whole bunch of stuff which is happening for every single HTTP2 request that we want to try and eliminate where possible. So our allocations are really just our gRPC stuff that our app is doing and not the stuff which Kestrel needs to do. So the way we did that is we introduced the pooling of HTTP2 streams. So let me jump into the source code. So here we've got our HTTP2 folder. This is where most of the HTTP2 implementation in Kestrel lives. And we've got this HTTP2 connection. So when our client connects to our server, we'll get a connection created, and then we start processing frames. So this particular method I already have open is where we process a header frame. So a header frame is where a client will send request headers and the server then processes them. And the header frame is important because once we've finished processing it, we start a new stream. So once we have requests, the headers for a new request. We allocate a stream to then manage the lifetime of that request. So a whole bunch of error checking happens here. We check state a whole bunch more. We do some processing until we get to this point where we're ready to start a new stream, which is helpfully called getStream. And if we jump into this, the code I'm viewing right now, this is .NET 5. This is after we've made the improvements. But previously in .NET 3, we would always just create a new stream. So we got some new headers for a new request. Let's create a new stream and all the types which sit on it. Now what we do is we have a pool of streams. So this pool is streams that we've previously created and have served an HTTP2 request. And then once we've finished with the stream, we return it back to this pool so it can be reused. So we're sort of recycling and saving the planet inside our HTTP2 server. And if we successfully have a stream to use, we pop it out of this collection, we initialize it with a new ID, and we start using it. So this is like just the tip of the iceberg of what is happening to support stream reuse. But this is like the core concept, is rather than creating something every time, we're attempting to reuse it. So if I jump in a bit further to look at some details more, let's look inside the HTTP2 stream. When we create, oops, I've got the wrong file open. When we create a HTTP2 stream, we need to initialize all the types that are hanging off it. So we've got this initialize method, and we set a bunch of values back to what they should be for when a stream starts being used. And now when this happens, we check to see whether it's the first time a stream is being used. If it's the first time it's being used, then some types that are sitting on it happen to be null, in which case we allocate them. So in this case, we're allocating some types for managing input and output flow control. Our output producer, this is our request body pipe, and this is our output pipe. But if we've already used the stream, rather than recreating all of those things, we just reset them. And each one of these types internally then has some code to handle resetting all its state back to the right value. So one of the other things we need to do to make this work is we need to ensure that we only reuse a stream that is safe to reuse. Mm-hmm. So an HTTP2 request could fail for a number of reasons. And if it didn't gracefully complete, we don't want to attempt to reuse it. Because if that request fails because it went into a bad state or it did something wrong, like it was aborted, we don't want to attempt to reuse it and then have another error pop up that we have no knowledge about, and it's very hard for us to debug, because the only reason that request failed is because the request before it failed, and sort of figuring out those kind of dependencies is quite difficult. So we have this can reuse flag, and with this flag we check when we're completing a stream. So we've got this complete stream method. We check some state on the stream to see whether it's safe to reuse the stream. Was the stream aborted? Okay, in that case, we don't want to attempt to reuse it. Did its response gracefully complete? If it did, then it's safe. So if both these things are true, then we know the stream is safe to reuse. Otherwise, we just throw it away and we create a new one. Better to be safe than sorry.
Yeah. You mentioned the case where things can fail due to like dependencies. Is there something similar to like distributed tracing? I've seen that with like other microservice applications, and there's a W3C distributed tracing spec and stuff. Is there something like that for gRPC?
For gRPC, yes, certainly. So gRPC has support, and it also has its own particular metadata for open telemetry. Open telemetry, yeah, that's the word. So when an open telemetry is being collected, gRPC requests and responses will have its own metadata. So it will say what gRPC method you're invoking, and also include the gRPC specific status, which is slightly different than an HTTP status.
Very cool.
So here is where we are removing the stream from the connection. So we're in the HTTP2 connection. We're removing the stream from it. And at this point, we check, can we reuse the stream? If we can, attempt to return it. And then we pull it. Otherwise, we dispose it. And the next thing I'll talk about is when we're pulling something, we want to put a limit on how many we're going to allow ourselves to pull, because we don't want to accidentally pull thousands of streams we've previously used before and have memory grow out of control. So for that reason, we have a limit on the stream pool size, and we only pull something if we're lower than this limit. Otherwise, we just throw it away. And the final thing I'll mention is we also have time-based expiration of pulled streams. So something which can happen with an HTTP2 connection is you could visit a website and you download all the content at once. So you might have 100 concurrent requests going on. And once all those requests finish, all 100 streams will go into the pool. Now, it's quite possible you never visit that website. You never browse to a different web page or make any more HTTP requests to that particular connection, in which case all those pulled streams are just sitting in memory. They're doing nothing. It's just wasteful. So for that reason, we have a timed-based expiration, where if a stream has been sitting in the pool for longer than this configurable number of ticks, then we just expire it out of the stream pool for you. And the way we do that is within Kestrel, there is this concept known as a heartbeat. So every 1 second, Kestrel will just take a look to see is there state that should be updated based on time. And on that 1 second interval, it will inspect this stream pool to see if there are streams that should be removed.
How much of object pooling did you have to write yourself versus what's built in to just .NET Core in general?
In this case, this is something we wrote ourselves, but it's not very complicated. It's just a stack. It's just a stack of streams that are just it's just a regular .NET collection. Just because although I'm talking about multiple things happening in parallel, this is one of those cases where all the logic is single-threaded when we're working with the request. So we don't even need to do any locking when working with this. So there isn't a need for a special collection type. You compare that to something like renting array pools, like renting arrays, and that will probably be happening from a static collection. So various locking needs to happen to ensure that two people don't rent the same array at the same time. Well, we don't really need to worry about that here.
Okay.
Okay, so those are all the changes we made. Well, some of the changes we made. And this is our previous results with that sawtooth pattern. And now if we take a look at our .NET 5 results, we can see that sawtooth pattern has disappeared. And now we have a just gently increasing slope of allocations. Now, allocations are still going up. GC is going to happen eventually at some point, but we've reduced the need for at least any GC to happen during our 50,000 requests. So this is the same 50,000 gRPC requests, just to a .NET 5 server compared to a .NET Core 3.1. And
now, it looks like the slope dropped off 3/4 of the way through.
Up here?
Yeah. Is there a reason for that, or is that?
Yeah, we finished processing the 50,000 requests.
Oh, okay. Right.
Yeah, so
okay.
this is the point where we finish doing any work and the server just stays constant from this point.
Got it. Okay.
And now if we take a look down at our list of allocations, that server call context now happens to be the #1 allocator, and everything else has to do with gRPC. So this is a gRPC message. This is the task which we're returning from our grpc method, another message, some internal stuff. So pretty much all the big allocations that are happening are now related to grpc, is what we want. So we want allocations to be related to our app and grpc rather than related to just HTTP2 stuff.
Wow.
Yep. So that's 92% reduction.
That's incredible. A question on well, I don't know if it exactly fits in, but question how much of this, like, can you use the Protobuf Serializer without grpc? How separate are those things?
They're completely separate. So grpc just happens to use Protobuf. Protobuf isn't tied to grpc. One of the nice things about grpc tooling is it will automatically code generate Protobuf messages for you. If you're using just the Protobuf serializer by itself, you'll need to generate those types manually from the command line. And an alternative to that is there's also a library called Protobuf-net. So it's written by someone in the community, and that one actually doesn't use code generation at all. It uses reflection instead.
While we're talking about that, can you use JSON serializer, deserializer with grpc?
You could. So there are extension points for doing deserialization and deserialization of messages. So the messages with grpc, like it's just a blob of data. So that data could be grpc, it could be JSON, it could be text, it could be just plain old binary. You could send an image via it, but most people are sending Protobuf messages.
Okay. And here's a more geeky one. Are related allocations contiguous? I'm going to pretend like I'm sure I know what that means. All the allocation contiguous memory.
I'm not quite sure about that. Like, obviously, if you're allocating an array, that array will, like, all the like slots in that array will be contiguous. But I'm not sure, like, if you just knew up a bunch of objects in a loop, how those would get allocated.
And I'm not sure why it would really matter at all. I mean, if you like,
there are performance benefits around, like, having your memory, like, closely grouped together. So I'm like, this is when I talk about different skills when it comes to doing performance analysis and improvements, like, that would be detail I don't really work on, and you'd probably bring in someone who's much more familiar with GC or the runtime to do those kinds of improvements.
Paging Stephen Taub or something.
Yeah.
But those
or Ben Adams.
Yeah, there you go. But it seems like in general, what's nice with the level you're working at is I don't have to worry about that. I can write grpc code, and then it's generating client code, and it's keeping things up to date with that. And that's something we looked at recently too with the connected services. When you generate clients, like, you can regenerate and update your clients from that contract, right? So if I update my proto contract, then it'll regenerate my client as well. And so then I can focus on writing business logic and not worrying about the plumbing. And
like, all the, like, we try and focus on, like, making the low level parts of .NET and ASP.NET Core fast, so that CPU time and memory is available for your apps. That's the goal.
So this is interesting here from Alfred, and he's asking if since one of the signals to indicate a stream can be reused is the fact the previous connection wasn't aborted. Is there a way that you can prevent an actor repeatedly aborting to defeat pooling? And just generally, like, how much do you have to worry about, like, a bad actor, and, like, managing clients, poorly behaved clients?
Well, it's not necessarily the previous request, but aborted and connections that weren't gracefully closed just won't get pulled. Like, it's not really an attack. It's just the requests wouldn't happen to take advantage of the extra efficiency that we've added to Kestrel. So I wouldn't describe it as an attack, but like if you're worried about
just poorly
performance,
behaved, I guess, is a better word for it, right?
yeah, like if you're worried about performance and a lot of the HTTP requests that are coming into your server are failing for, and by failing I don't mean they're gracefully returning a 404 response. Like that's not a kind of failure I'm talking about, but like we're throwing an exception and they're aborting a request before they've read all the content. That's the kind of non-graceful failure I'm talking about. Like if that's happening, like your performance is probably already bad, and you should focus on fixing that before doing other analysis.
Okay, we have a trick question from this Sebastian guy. He says, how big can the pools grow and how fast will they shrink?
So the pool maximum size is 100. So we will pull up to 100 streams on a single connection, and it will start shrinking if a stream hasn't been used in 5 seconds. So 5 seconds sounds quite short, and maybe it should be slightly longer. We haven't like done a huge amount of analysis on that. But like if you've got a steady number of requests, like thousands of requests coming into your server per second, that's the point where you start caring about performance and you start taking advantage of this pooling. While if you've got one request coming in every 10 seconds, like the cost to allocate a stream is and all its related types is really nothing, and you shouldn't worry about it.
All right. A question on hosting multiple gRPC services in the same app, but on separate transports. So service 1 on domain socket, service 2 on TCP.
Yeah, you can do that.
All right. Easy enough. Okay. Let me see one here. Timeline or a roadmap for using gRPC with Service Fabric within the cluster and for external clients.
I have no idea.
That's a separate thing, right? The Service Fabric thing.
Yeah, like I have no idea what they're doing, and I probably wouldn't be able to speak for their team.
Okay, cool. Wow. Okay. Yeah, no, I'm just trying to think through all this. This is really interesting, especially like I've been doing more stuff with microservices lately and thinking about being able to like high performance microservice communication between different services using gRPC. And then like looking at these performance improvements, that would be amazing to just say like, boom, all my microservices just got 92%, less allocation and stuff.
Yeah.
Wow. So this is these are updates for .NET 5. And then what are some of the things that you're thinking about and looking at with .NET 6? Is there much new stuff kind of in the works there, or?
.NET 6 stuff. So I had a second demo, but we haven't got time for it. But I'll jump ahead to the slide.
Oh shoot! I talked too much and didn't get the SIMD demo. Yeah, actually, you've got enough time for a quick demo. That's fine.
Okay, a very quick demo. So SIMD, for anyone who's not familiar, stands for Single Instruction Multiple Data. Basically, it's about doing more on data with less instructions, so your CPU can be more efficient. So this is something which has been done in Protobuf and our Protobuf Serializer. So now I've got the Protobuf solution open. I don't have a profile of this, but we identified that write string was a hot path, which makes sense because when you're serializing JSON or Protobuf or any message type, generally strings are probably the majority of the data. So we're basically taking a string, we're wanting to write it to this buffer as UTF-8 bytes. We'll ignore all of this and we'll focus on this particular loop. This is the hot path loop which we identified. And although this looks very simple, this particular line, there is a bunch of stuff happening which doesn't need to happen. So we've already previously identified that this particular string value is all ASCII, And because it's all ASCII, it fits in a single byte. So basically, we're looping over the characters in a string, and we're casting it to byte, and we're putting it in our byte array slash byte span. So there's a bunch of stuff happening here which doesn't need to happen. There are these accesses of indexes, and each time you do one of these, typically .NET will just verify that you're within the bounds of your buffer or your array, because if you go outside, then you can start reading or writing random memory, which is very bad. And also casting this byte, there's probably some checking to just double check that the char that you have actually fits within a byte. But we already know that. We've already validated that up here. So this was the hot path. We'll get rid of this. And what we introduced in a newer version of the Protobuf Serializer is, let me simplify a bit, is we have some more advanced APIs that live in .NET. So we've got this memory marshal.getReference. This sort of gets a reference to the very first character in our string. And then we're doing the same thing with the first byte in our buffer. What we can then do is use some unsafe APIs to access values to and from these arrays, and we can read and write to them without having to do bounds checks. So obviously you want to double and triple check that you're not going to accidentally read off the end of an array, because that would be very bad. But doing this quickly allows us to remove those bound checks. And obviously this is unsafe, which is indicated by this unsafe keyword. So this is step one. Step two, getting more advanced. We're going to process 4 characters at a time using SIMD. So rather than doing this byte by byte that we're doing down here, so we're still casting to a byte, chars to a byte one at a time, we're going to do 4 at once by using SIMD. So first thing we're going to do is we're going to take our chars, so our reference to the string value, which we're reading as chars, and we're going to, instead of chars, read them as bytes. So this allows us to reinterpret the data in an unsafe way to read the chars as if they were bytes. And then we're going to process 4 at a time. So we're going to loop over this data, and we're going to just double check we've got at least 4 characters remaining. We're going to get the offset of our current position based on this current index. We're then going to read the source chars, which we're now reinterpreting as bytes. We're going to read it as a ulong. So this is a 64-bit sized data type. So that will fit 4 characters inside it, because each one of those is UTF-16. So they each take 16 bytes. And then we're going to set them 4 bytes at a time. So I've got a method here, which you might be wondering what's going on in this method. This is where we start doing the SIMD logic. So what happens is we check to see whether the current CPU supports it. So in this case, we're checking, does it support SSE2? If it does, we use some SIMD intrinsics to process all 4 characters simultaneously and then write them at once. If SSE2 isn't supported, we then check to see whether you're on an ARM computer. If you're on ARM, then it has its own equivalent instructions for doing the same thing. And then if we have neither, then we'll fall back to a non-SIMD approach. And in this case, because byte order matters, we'll just check this guy. And then after doing that, we will set the values. So basically what's going on here is we're taking UTF-16 values, which is a char. So this char represents UTF-16 character. If we zoom in a bit, we can see that there. And we're narrowing it down to 8 bytes, we've already confirmed that it fits within 8 bytes. We just want to do this as quickly as possible. And the way to do that as quickly as possible is to remove all the branching going on. So previously, when we were doing bounds checking, that was branching. When we were checking again that a char fit into a 8-bit byte, that was some more branching. But by getting rid of all of that and doing this here, you'll notice, let me just say, all of these if checks, they'll get removed when JIT happens, because these are constant. Like this is like, if you're on ARM, JIT will just remove this for you. Likewise, if neither ARM or SSE2 is supported, JIT will remove this for you. Likewise, JIT will see this check and it will remove either this or that for you. So all these if checks disappear. So basically what we're aiming towards is just to remove all the ifs, so all the branching related to bounds checking data types. We just want to focus on converting our 16-bit values down to 8 bits.
And then when you do, and in most cases, you're going to have support for SSE2 or ARM, and then I mean, and then you're going to get you're 4 times faster. Like you're processing 4 character or 4 at a time instead of 1.
Yeah,
so
it's not necessarily 4 times faster, but it's certainly faster.
Wow.
So even if SIMD isn't supported, like you can see this comment here, it's even if it's not supported, it's still faster. Like doing this is still going to be faster.
Wow.
So I've got the results, which we'll jump to. So our baseline with that for loop plus casting, that was about 11 milliseconds. This is running this on top of multiple kilobytes of ASCII text. If we switch to using that ref and unsafe and processing 4 chars at a time without SIMD, we drop down to about 6 milliseconds. And then if we add in SIMD on top of that, we drop down another 0.8 of a millisecond. So our initial value, we've pretty much halved it by using these advanced techniques.
That's crazy. It surprised me when I looked at the cases. I was like, well, hopefully I get one of these SIMD instructions because that's what's going to do all the work. But this is amazing. You get most of the performance just by like writing smarter code.
Yeah, I think it might be a lot of the bounds checking, which was happening in that for loop. Like there's 2 arrays and you're getting and setting from both of them, and then like it just adds up. So I think that's where probably most of the gain comes from. And then SIMD, it's just like the cherry on top to knock off another millisecond, which like seems small at this point, but that's probably like 20% faster.
Yeah,
which is certainly not bad.
That's nice. For writing this code, is there like some sort of guide or something for like you only want to do this in a hot path, right? You don't want to be writing that kind of code all the time. But if you do get to a place where, hey, I'm writing a service and this is my hot path and I need to optimize it, how what's the best thing for doing what you just did there?
I don't know. Like I did find one guide that someone wrote. Like there was a blog post. I don't have it handy. But yeah, writing this sort of code is tricky. In fact, if you take a look at the Protobuf code, you'll see I actually copied this directly from .NET Runtime. So this particular method, which is doing this logic, the .NET was doing the same thing. When you take a UTF, like when you have a string and you want to convert it to UTF bytes with the like encoder.utf8.getBytes, this is potentially executed internally. So I did a shortcut and I just copied this. This code up here, I just sort of figured it out myself. I don't really have a recommendation. Like this is pretty advanced stuff. It's also relatively new stuff. I'm not sure of the best way to learn it. But when you're doing it, just be careful because this is unsafe. You need to be checking your indexes and checking your links even before you do any of this stuff.
My big takeaway is to be thankful to you for writing this code so I don't have to. And it's just it's just part of gRPC now. So Protobuf. Yep. So that's cool.
Yep. And I'll just do a summary of what's new in .NET 6 with gRPC. So gRPC retries is something I've just finished writing. Perhaps I might talk about it in a future community stand-up. Another thing is support for the gRPC client on .NET Standard 2.0. That's now done. If you're in .NET Standard 2.0, your implementation, your .NET implementation might not support HTTP2, but you can always fall back to using gRPC Web. gRPC running on top of HTTP3, that's work in progress. So I'm in the middle of adding support to HTTP3, for HTTP3 to Kestrel, and I have a basic hello world of gRPC working. So progress is being made there. And then one which hasn't been started yet is client-side load balancing. So that's configuring a client to be able to talk to multiple endpoints, and it will then use load balancing strategy and health strategy to pick healthy servers. So you can do load balancing directly from an app without having to use a proxy in the middle.
Wow. Wow, that's cool. All right. Well, that is a ton of stuff. I kept you late and I made you show the extra demo, but I'm selfishly glad. I love SIMD stuff, and I've been following along like since the early days when they're looking at it. It's cool to see that like actually doing something there. So for people that are interested and want to keep up, I mean, of course they can follow on Twitter. And then there it is. You know the questions I ask.
Oh, yeah, wow, so I'm a big believer in documentation. So there's lots of docs available. And if you read the docs and you want to see examples, there's also lots of examples.
I will paste a link to that in the chat. That is one step ahead of me. That is awesome. Well, wow, those are really cool. I mean, that was a lot of great stuff. Thank you so much. Please, let me know next time you got something cool to show off, and we'll be happy to have you back on.
Yeah, maybe after, just before or after .NET 6.
That sounds great.
In November.
All right. Awesome. Well, thanks everyone. This was a great show. Appreciated all the cool demos and stuff, James. And we'll talk to you soon.
Yep. Thanks. Bye.